This module will briefly review some of the mathematical concepts that will help you understand the topics covered in this statistics course. In this video, we'll be focusing on 5 concepts: factorials and summations, the equation of a line, and the exponential function, as well as the natural logarithm. So jumping right into factorials. Factorials are denoted with an exclamation point, as shown here. The formal definition for a factorial, and I'll repeat this, is that it's the product of all positive integers less than or equal to the number. Again, it's the product of all positive integers less than or equal to this number. Now, if I say that another way, that's like saying that when you take the factorial of a number, you're multiplying all the positive whole numbers between that number and the number 1. So let me illustrate that with an example. 3 factorial. What's 3 factorial? It's 3 times 2 times 1, and that's equal to 6. Okay, the key takeaway here is that 3 factorial is simply a number. 3 factorial is equal to 6. Let's go over another example. What's 6 factorial? So we're going to be multiplying all the numbers between 6 and 1. So that means 6 factorial is going to equal 6 times 5 times 4 times 3 times 2 times 1. And we're going to do a little bit of math here. And we're going to figure out that 6 factorial is equal to 720. Again, the big takeaway here being that 6 factorial is simply a number. It's equal to 720. It's you can think about it as if it's another way of writing 720. One thing to know about factorials is that you can only take the factorial of a positive integer. You can't take factorials of negative numbers and get a real solution. One thing you'll have to remember about factorials is what 0 factorial equals. 0 factorial equals 1. Again, 0 factorial is defined as 1. Before we move on to summations, one last thing I want to go over with factorials is a trick for how to simplify them. Let's say you come across a problem, 13 factorial divided by 10 factorial. Because you know the definition of a factorial, you're thinking to yourself, gosh, these are going to be really large numbers. I'm going to have to multiply 13 times 12 times 11 times 10 all the way down to 1. Do that again on the bottom. Well, you can also rewrite this top part, but instead of going all the way down to 1, you can stop here and finish off this expression with 10 factorial. And the reason I'm going to do that is so that I can cancel out the same expression on the top and bottom of this fraction. And remember, I can do this because 10 factorial is a number. I don't know what number it is off the top of my head. It's a very large number, but I can cancel that. And that leaves me with something very manageable, 13 times 12 times 11, which happens to equal 1,716. So this is just a trick for simplifying factorials if you ever come across a problem like this. Summations are expressed with the capital Greek letter sigma. Okay, and whenever you see a summation symbol, I want you to focus on these 3 areas. Okay, this first part on the bottom of the sigma represents the lower bound of the summation. This top part, number 2, represents the upper bound. Very intuitive. And then this third part on the side is the expression that you're going to be summing over. And let me illustrate what I mean by that with an example. Okay, so let's say your index variable right here, your lower bound, is going to be 1. We're going to be going all the way to 6, and we're going to be iterating over I. What does that mean? Well, it means we're going to start at 1, and every time we add a term to this expression, we're going to iterate I by 1 until we reach 6. So that means 1 plus 2 plus 3 plus 4 plus 5 plus 6, okay? And that equals 21. Okay, just like with factorials, this complicated looking expression is just a number. It's another way of writing 21. Another key point here is to realize that I'm adding all of these because these are all equal to I, and that's the expression that we're summing over. Okay, let me illustrate this with another example. So very similar to the last one, except we're going to be subbing over 7i. Okay, so this is going to look like this. we're going to start at the lower bound, okay, and end when we reach the upper bound, whatever that definition is. In this case, it's still 1 and 6. So what we're going to do here is multiply 7 times 1, 7 times 2, okay, all the way until we reach 7 times 6. And you might realize that you can take out the 7 from this expression, okay, to give yourself something that looks like this: 7 times the quantity, 1 plus 2 plus 3 plus 4 plus 5 plus 6. Of course, and because we did this last problem, we know that that's 21. So this expression right here results in 7 times 21. Okay, so let me rewrite that in another way. So that results in 7 times this summation. If you'll look at these two carefully, what you'll realize is that all I did was move this 7 to the outside, okay? This illustrates one property of summations. There are multiple properties. I won't go into them in this video, but I just wanted to give you a taste of what knowing these properties can do and how they can help you simplify much more complicated expressions. One more example with summations. Now let's imagine that you have some data. Okay, let's imagine that you have 5 data points labeled x1 to x5. Okay, and let's imagine that these values are 2, 4, 6, 8, and 10. Okay, we call this, we say that this data is indexed, and what that means is that this first point, okay, corresponds to x sub 1, the second point corresponds to x sub 2, etc. And each of these points corresponds to an actual value in the data set. So I can use a summation to sum either part or this whole set of numbers. Okay, and let me illustrate that. Let's say with something like this. Okay, so what is this expression going to equal? Well, if I write it out, this is going to be x sub 3 plus x sub 4 plus x sub 5, which corresponds to 6 plus 8 plus 10, which is 24. Okay, so this illustrates a more practical example of how you can think about summations and how they can be helpful to you when thinking about large sets of data. Probably the most common form that you'll encounter when you're looking at the equation of a line will be slope-intercept form. And that will look like this: y equals mx plus b. You've probably seen this before. So m represents the slope, b represents the y-intercept. Okay, that's the point at which this line intersects the y-axis, and y and x are, of course, the y-coordinate, the corresponding y and x coordinates for points that lie on this line. Now let's illustrate what we just went over again with an example. Let's say y equals 2x plus 6. Now if I ask you what the slope is, you're going to tell me that the slope is 2, because this 2 corresponds to this m. Okay, and similarly, if I ask you what the y-intercept is, you're going to tell me that it's 6 because it corresponds to b. More accurately, the y-intercept in this case is going to be 0, 6. Now let me talk a little bit more about the slope. So slope is defined as the change in y over change in x. And another way of remembering that is by remembering this phrase, rise over run. And again, I want to illustrate all these concepts with the example from before, and this time I'm going to graph this. So this is your y-axis and this is your x-axis. So we know that the y-intercept is 6. So I'm going to pick this point to be the y-intercept, and I know that the slope is 2. So I'm going to go up 2 points for every 1 point that I go over, or also do the opposite, go down 2 for every 1 point that I move to the left. 1 unit I move to the left. And connecting these dots gives me the graph of this line. Moving on to the exponential function. The exponential function is denoted like this with the letter E. Sometimes you might see it written like this. Don't get confused, these are the same things. It's important to note that E is a number. E is equal to 2.71828, etc., etc., etc. And so if you find yourself forgetting this, it might be useful to remember e to the x as approximately equal to 2.72 raised to the x. Now, if you want to check to make sure you're doing this right, e to the 3 will equal 20.085, and you can use that in Google or your calculator to check that you're doing this the right way. All the normal rules of exponents also apply to the exponential function, and what I mean by that, let's say e to the 0, any number raised to the power of 0 will equal 1. Also, any number raised to a negative exponent will be 1 over that number raised to the positive exponent. And that's where I want to leave the exponential function. Please do note that the exponential function is used very commonly in the sciences, and that's because it has some appealing mathematical properties that allow scientists to model behavior they see in nature very, very well. Moving on to the natural log, you can write the natural logarithm like this, log base e of x, or more commonly as ln of x. And the main idea that I want you to take away with regard to this course is that the natural log and the exponential function are inverses of each other. And what that means is that they undo each other. So the natural log of e to the x will just be x, and similarly e to the natural log of x will also be x. And this is important because when we're doing certain statistical regressions, we're going to have an expression that looks like this, and we're going to want to know, we're going to just want to isolate what's inside the natural log, and so we're going to raise this to the e to get that middle part. All the rules about logarithms also apply to natural log, and I'll illustrate a few of those here. So the log of 1 will always equal 0. The log of 0 will always be undefined, and you can't really take the natural log of a negative number. At least you won't. That won't result in a real solution. So that concludes this math review, and I hope you found it useful.